Hi, welcome to the world of vector space. Before moving on to vector space, let me define what a field is. So field is any set in which the addition and the multiplication is defined. The following property are satisfied. Say A and B. Let's say we denote the set by F for the field. Say if A and B they are the part of the field, then they should be closer under addition and multiplication. A plus B should also belong to the field, and A times B also should be inside the field. They should be commutative. A plus B equals B plus A, and A times B should equal B times A. They should be associative. A plus B plus C should be equal to A plus B plus C, and same thing with the product. Let me not put this multiplication sign here. I'll just write BA for the B times A. So AB times C equals A times B times C. And there should be inverse and identity. The additive identity, that's 0. A plus 0 equals A. And inverse, there should be some B that should give A plus B equals 0, and we write B as negative of A. Is the additive identity. This is the additive inverse. And same thing with the multiplication. A times 1 equals A, and there should be some B, so the A times B equals the identity, the 1 itself, and we write B as A inverse. And multiplication should distribute over addition. I'm going quite fast in this because I'm assuming that you already know this. A times B plus C should be AB times AC. If these are satisfied in any set, it could be set of real number, it could be set of rational number, it could be set of complex number, or something else, some other sets. If these are satisfied, then we call that set a field. So while talking vector space, we'll be strictly looking at the real vector field. That's a set of real numbers, and sometimes we'll be looking at the complex number as well, but that's going to be only in few examples. In most of the cases we'll be looking at the real field. Let's go for the vector space. And what is a vector space? Vector space is a set, and it operates under a field. It could be real or complex field. We'll look at that in a moment. It is about abstract linear algebra. We are defining vector space not on what it is, but based on the properties. Vector space is a set, and let V, U, and W be the element of the vector space V. Then in order to be a vector space, it should satisfy the following properties. U plus V equals V plus U, commutative addition, and the sum belongs to the vector space, the vector itself. It's called closure property. Associative under addition, U plus V plus U plus U plus V plus W should equal U plus V plus W. And we have same property for the scalar multiplication. Let's say alpha belongs to the field, then alpha and beta belongs to the field. Then we have similar property. The scalar multiplication of the alpha times the scalar multiplication of beta times v should be alpha beta times v, and it should also be fall under the vector space v. We have additive identity, the 0. We have additive inverse, and we denote the inverse as negative of v. That should give the additive identity. We have multiplicative identity, 1 times v equals v. It is simply the scalar multiplication. We are multiplying alpha and beta are the parts of the field, they are scalar, and v the vector. And we have the distributive properties. Let's note that alpha belongs to the field, v equals alpha u and alpha v, and alpha plus beta times u equals alpha u and beta u. So if any set satisfies all these properties, any set v satisfied all this property, then that set v is called a vector space. And this alpha, beta, these are the field. It could be real number, it could be complex number. If these properties are satisfied, if f is real, then we call if f is real number, we call v as real vector space. And if the field is a complex number, the complex plane, then we call v as complex vector space. Some examples of the vector space. The first example that should come to your mind is the ordered pairs x comma y, which you denote as the vectors. X is where x and y are real number. Let's talk about real vector space here, are the real numbers. Then all these properties are satisfied for the set. And let's try to be more formal. If A is the set of all x comma y, where x comma y belongs to a real number, then A is a vector space, or it could be a 2 by 2 matrices. Let's say B is set of all 2 by 2 matrices A, B, C, D, such that A, comma B, comma C, comma D belongs to a real number. It is also a vector space, and the definition of the addition would be the component wise addition. If we have two elements of the A, the addition would be adding the respective components, and the scalar multiplication is multiplying over all the components. The same here. If that's the case, then these are vector space. Complex number, you could write them as ordered pair or a plus bi. If the addition is component wise addition and multiplication is scalar multiplication for all the component, then this is also this set of complex number is also a vector space. Real number itself is also a vector space, because we can add two real numbers, we can times the real number by a scalar, the real number, and they are all defined and the properties are satisfied. So this is also a vector space. Having looked at the vector space, let's just limit in the color so as to make you feel more colorful. Okay, Let's look at the subspace. We have the vector space V, where V is the vector space, and let's say we have W. That's the subset of V. W is a subset of V, and W is called subspace if W is also a vector space. Any W that's subset of V is subspace if is vector space in its own right. And the way we test whether W is a vector space or not, the first is it should be subset of V. That should be known, subset of vector space. Then the way to test this is it is a vector space if the 0 vector belongs to W. Second, if two elements, let me not write A, let me write W1 and W2. If these two elements are, if these two are members of W, then the sum of these two also should be the member of W. This is the sum of vectors is also a vector, and this should be under W. We don't need to check all the 8 or 9 properties. If we check 3 properties and we know that W is subset of some vector space, then we are done. Next is, let's consider alpha belongs to F, then also should belong to W. The scalar multiplication of W1, any element that inside the W, if the scalar multiplication of it is also contained inside the W, then it is also a vector space, sub-vector space. These are the 3 properties, and there's one way to test these 2 properties at once. So this is 0 should belong in W. That's one. These two can be summarized as a single property. Say alpha 1 and alpha 2. Alpha 1 should be could be anything. Alpha 2 could be anything. For any alpha 1 and alpha 2 that belongs to F, if alpha W1 plus alpha W2, if that belongs to W, then it is a vector space, provided the property 1 is also satisfied. If this is satisfied, then 2 and 3 is satisfied. Let's look at a few examples of subspace. Examples of a subspace. Say you have a vector space that's R3, or in other words, it's a set of triplets, 3 coordinates x, y, and z. And if this is a vector space, then the subspace of this vector space would be V itself. It is also a subset of V, is also a subset of V, and that is a vector space, so V itself. The 0 vector is also a vector space. It's quite easy to see. If you add, there's only one element inside this, so if you take 0 vector and another 0 vector, add those two 0 vector, you will get the 0 vector that's inside this. And if you times this 0 vector by some scalar multiple, it will also be a 0 vector that's inside this. And the first property was that 0 belongs to the vector space. Yes, it belongs. This is another vector sub-vector space. Another sub-vector space would be set of all x comma y comma 0, in which all the z components are 0 and x and y exist, and x and y component can be anything. This is also a vector space, and this is vector space in R2. Another vector space could be x comma 0 comma z, Another vector space could be set of all 0 comma 0 comma g. This is one dimensional vector space, and this is the subvector space of this. So all the subspaces of the R3, they are the subspaces of this are R3 itself, the 0 vector, all the R2s passing through the origin, and all the R1s passing through the origin. Okay, having defined the subspace, let's look at few properties or few operations of the subspace. Let's look at the sum and the direct sum of subspace. What's the sum? Well, say V1 and V2 are the subspace of V. This is the way how we denote the subspace. If in order to say U is the subspace of V, we write this symbol that looks like the less than or equal to symbol. Say V1 and V2 are subspace of V, then sum of these two subspaces V1 and V2, they are defined as, that's written as V1 plus V2, is set of all the elements for which set of all V2 such that V1 belongs to V1 and V2 belongs to V2. So what does this mean? This is set of all the possible sums of the elements of this and this. You have some element of V1, some other element of V2, you add those two and put it here. You take all the possible sums of these two, and that set is the V1 plus V2. That's the sum. And there is a property. If V1 is the subset of V and V2 is the subset of V, then sum of these V1 plus V2 is also subset of V. And this sum is called direct sum if for every V1 plus V2, for every element in V1 plus V2, we can write that as sum of two vectors. That's the first vector is from the first V1 belongs to V1 and small v2 belongs to v2. So the sum means that all the elements of this can be written as the sum of the first vector from the first vector and second vector from the second vector. And it could be, there are many ways of writing, there could be many ways of writing this. Say v1 is also a r and v2 is also a r, and let's say we have an element inside this 5. So it could be written as 1 plus 2, 1 plus 4. It could be written as 3 plus 2. It could be written as 2 plus 3. There are many ways of writing those. But if there is only one way of writing those, there is only one way of writing v1 and v2, then we call that as a direct sum, not the sum. And we denote that as the circle above or top of the plus sign. That's how we denote this. And a sum is called direct sum. direct sum, provided any element that belongs to the sum v1 plus v2, then there is unique way of expressing w as v1 plus v2 such that v1 belongs to v1 and v2 belongs to v2. So any element, as we already know, I'm saying that again because many people get confused here. Any element that's the element of sum, then we can write that as the sum of the element of v1 and sum of another element of v2. But in general, it doesn't have to be the only way of writing that. So there could be many ways of writing. 1 from this the first set and 4 from the second set. 3 from the first set, 2 from the second set. 2 from the first set, 3 from the second set. There were many ways of writing that. But if there's only one way of writing that and no other way, then we call that sum as a direct sum. And there is a way to test whether a sum is a direct sum or not. This is true if and only if the vector space, the vector subspace v1 of the v, if we take the intersection of these two subspaces and the only common element in these two is the 0 and nothing else, the 0 vector itself, then this condition is satisfied. So if this is true, then, and obviously v1 and v2 are the subspaces of v, then v1 plus v2, we can write that as v1, either v1 plus v2. We can write that as direct sum of v1 and v2. Let's look at the linear combination of few vectors. Say you have few elements v1, v2, vn, all the way up to vn, and they belong to the vector space v. Then any combination, any linear combination of these, okay, it might be quite confusing to you. I will tell you. Say a1, a2, and they are scalars, part of the field. So any combination of this, any combination of a1, v1 and a2, v2, v1 to vn are already defined. That's the set. a1, a2, an, there could be any scalar. So any vector u that's obtained from adding the scalar multiples of these vectors is called linear combination of these vectors. And the set of all possible linear combinations of v1, v2, vn is known as span of this vector, span of these vectors. So any scalar multiple of these vectors added together, that's a linear combination of these, and the sum of all the possible scalar multiple and addition, all possible use, is known as, the set of all possible use is known as the span of these vectors. Let me see the color. And Span is a subspace in its own right. By subspace I mean subspace of V. Okay, now we know what is a linear combination. Let's talk about linear dependent and linear independent. Linear dependency. Say you have list of vectors u1, u2, u1. They could be, let's say they all belong to a vector space V, some vector space. Then these vectors are said to be linearly dependent if, let's say we have an equation where all the a's are the scalars, a1 u1 plus a2 u2 plus am um. Let's say we solve this equation. We don't know what a's are. So a1, we know what u's are because they are the chosen elements, and want to see if they are linearly dependent or not. And we write this equation: scalar multiples of these added together, that gives to 0 vector. So we are looking to find the solution of this equation. If the only solution to this equation is all ai is equals 0, if all the a's are 0, then obviously this is satisfied. If that is the only solution, then u1 to this set is known as, these vectors are known as linearly independent. If non-trivial, if all the a's are 0, we call that trivial solution. If non-trivial solution to this exists, then these vectors are linearly dependent. What is this? This means that this means that one vector of this can be written as a linear combination of someone else. For example, u1 can be written as alpha 1 u2 plus alpha m u1. Any vector can be written as linear combination of some other vectors if they are linearly dependent. If they are linearly independent, then we can't write one vector as the linear combination of other vectors. Now that we have talked about the linearly dependent or linearly independent, let's talk about the basis. Let's say we have a set of few vectors, those are element of V, u1, and they are element of V, the vector space V itself. These vectors or these elements are said to be bases of V if the following conditions are satisfied. The first is all ui's are linearly independent. It means that none of the ui's, u1, u2 or anything, they can't be written as linear combination of remaining elements. All ui's are linearly independent. That's the first condition. The second condition is if we take the set of all the combinations, all the linear combinations of this. In other words, span. Span is the set of linear, all the possible linear combinations of given vectors. Span U equals V. Then that is V. If that is V, set of all possible linear combinations, if that gives the vector space itself, then these elements are said to form a basis for V. They are known as bases. If this is a basis for V, then any element inside the V and W that belongs to V can be written as the linear combination of these vectors. W can be written as alpha 1 u1 plus alpha 2 u2 plus alpha n un. Then this is true. Okay, so W can be written as the linear combination of all the u's, and if all these are bases, that means these two conditions are satisfied, then these alphas are unique. This is the only way to write W as a linear combination of these alphas. There's no other solution, no other way to write that. So here are the few notes to make. Something could be misleading, just to clarify that. Okay, if I set some elements inside, set W spans V, this doesn't mean that W, the elements of W form the basis. This does not mean that W forms basis for V, and the reason for this is we can't be sure that they are linearly independent. They could be linearly dependent. One vector can be written as a linear combination of some other vectors. If that's the case, then we can choose any element from the V, vector space V. Then the way of expressing this as a linear combination of these vectors won't be unique, because these vectors aren't linearly independent. One vector can be written as the linear combination of some other vectors. Then obviously that won't be the case. We can't write an element. We can write those elements as linear combination of these vectors, but that won't be unique, and that's why these aren't said to form a basis. The reason for that is some vectors may be redundant, but this is really important here. So what can be done is, any spanning set can be reduced to a basis of V by removing the redundant elements. This will be clear after we look at an example. Let's look at one example. I'm running out of space. Say we have vector space R2, that's set of all x, y. Let's say we have this vector space. Then let's say we have a set 1 0 1 0 1 1 0 3 0 1. We have these 1 2 3 4 elements. We have some set, and if we take all the possible linear combinations of these 4 sets, it gives R square. But these 4 aren't all linearly independent. For example, this vector can be written as sum of this vector, and this vector. 0 3 can be written as 3 times 0 1. They aren't linearly independent. So what we can do is, we can take few redundant elements out and then form a basis. For example, 1 0 and 0, 1. These two form a basis for R2, 1, 0 and 0, 3. This forms a basis for R2, 1, 1 and 0, 3. However strange it might look at the first glance, this also forms a basis for R2. In fact, any two, obviously not these two, they can form the basis for R2. So what we have done, in order to make this basis, or this basis, what we have done is we have taken out the redundant elements. We have just left the linearly independent elements and formed the basis. We looked in the last part, thus the set of these four elements, they span the vector space, which is the R square, with the R2, but they don't form a basis because all these aren't linearly independent. So what we did was take out few redundant elements and then take only the linearly independent elements, and that formed the basis. For example, this was a basis, this was another basis, this was another basis. A basis doesn't have to be unique. 1, 0 and 0, 1, that's one basis. 1, 0 and 0, 3, that's another basis. 1, 1 and 0, 3, that's another basis. There can be many bases, but there is one thing common in all these bases, and that is number of elements in any basis for V is the same. Here all these bases have two elements. So now if we know that the number of bases is same for all the bases, number of elements inside the basis for all the vector space is same, we can now define the dimension of vector space. It is the number of elements inside any basis of the vector space. So now we have defined the dimension of the vector space. Okay, let's say we have a vector space V. Let me change the color. V is the vector space. Let's say dimension of V is, and that there are two things that we need to know. First of all, the set of m elements, where m is less than n, m linearly independent elements, can be completed to form a basis. All you have to do is plug in few more elements and that will give us a basis. And another thing that we need to note is, say we have the set of k elements where k is greater than n, and this is the set, and the set spans V, the vector space. So we have the set of the elements more than the dimension of the V, and the set spans V. What does this mean? At least one or few elements inside this set are redundant. This set is not linearly independent. So what we can do is, this set can be reduced to form a basis. And the way to do this is by taking redundant terms out. Okay, so linearly independent set of vectors can be completed to form a basis, or any spanning set can be reduced in order to form a basis. Okay, there is one important rule that you need to understand. Any set of and for any the dimension of the vector space and linearly independent elements or the vectors, however you write, and these vectors should be element of the vector space, so they belong to V. If we have n such linearly independent elements of V where any the dimension of the V, then n is the basis, then this set is the basis. Is the basis. Is the basis for V. Now let's look at few theorem. Okay. If U is the subspace of V, then dimension of U is less than or equal to dimension of V. If dimensions are equal, then U equals V. Vector itself can be the subset of V itself, and hence it is the vector subspace of the vector space. If dimensions are equal of the subspace and the vector space, then subspace is the vector space itself. Okay, let's look at few other properties. Before that, let's look at the intersection and union of subspaces. Say U and W are subvector space of the vector space V, then the intersection of that is also a subvector space of V, but let me write union by this sign so that we don't get confused with these signs. Union W is not the vector space of V, subvector space of V. And we have the dimension theorem. The dimension of U plus V, remember the sum I defined few minutes earlier. Go back and watch that again if you forgot. The dimension of U, dimension of V minus dimension of U intersection V. And if the sum is the direct sum, then dimension of U, a direct sum V, equals dimension of U plus dimension of V. Because we all know that if the sum is a direct sum, then U intersection V, the only element that's common in U and V is the 0. And if 0 is the only element, we say dimension is 0. Dimension of U intersection V equals 0. Thanks for watching. Hope you enjoyed this video. Please like, comment and subscribe, and stay tuned for future videos. Thank you.